Thanks. Hey, I am Ravi. I'm from Marvel, and I have Madhu. He's from Avis. Today we're going to talk about how we go about enabling the mirror and drop feature in SONiC, and particularly we'll emphasize on the need for standardizing this feature so that it can be in community SONiC. This is a joint work with Peter from Inmon, Juning from Edgecode, and Isaac, who's here from eBay. We'll have an overview of the feature mirror and drop. Then we focus on the challenges and the need for standardization to get this feature into community SONiC. Then we introduce existing open source components inside SONiC that can be used for this standardization instead of reinventing everything from scratch, and how we put all these components together. And then we'll look at the SONiC architecture, more references for information, and a call to action. So mirror and drop, this is a feature used to troubleshoot packet drops in a network. Switches and routers that support this feature generate a notification when a packet gets dropped in the switch. This notification goes to an external collector. This notification has a copy of the packet along with some metadata. The metadata will contain the switch ID, the switch at which the packet was dropped, the ingress port on the switch, the timestamp at what time that port, timestamp of the drop event, and the reason why the packet got dropped. With all this information, it becomes easy to understand which packet got dropped, where in the network, and why in the network, at what time. So mirror and drop is a well-known solution. It has been discussed multiple times in multiple years. It's been well-known, and it's an easy to deploy feature. But this feature is not there in community SONiC yet. And some of the main challenges that prevent this are there was no well-defined standard SI API configuration to configure the mirror and drop in a SI campaign switch. Also, the drop reasons for the reasons why a packet gets dropped, that depends much on the switch ASIC pipeline, and it could vary across switch vendors. Also, not just the drop reasons, the way these reasons are reported, even those have not been standardized. And to add further to this complexity, packets can either get dropped in the forwarding data plane or could also be getting dropped in the punt path, in the slow path, in the CPU or kernel stack. So we need a consistent view of packets getting dropped either in the hardware or in the slow path. And most importantly, network operators want this drop reasons to be standardized across different types of network operating systems. Not just SONiC, it needs to be consistent across other network operating systems. And today what we see is mirror and drop has been talked about, and it's being used, supported by vendors, but it's more like a premium feature. It's not in community SONiC, but each vendor has their proprietary ways of supporting mirror and drop. So we believe a standardized solution will be easy to get it into community SONiC, and all vendors can support a standardized version. And to go about this standardization process, what we first did a couple of years ago was we got the SI API model standardized in the SI community. So the SI has something called a telemetry and monitoring framework, which is a natural fit for the mirror and drop feature. We extended it to use generic netlink. So we had to add support for TAM to send reports in terms of generic netlink messages. And what this will allow is, it will allow us to align this drop reporting to what is there today in the Linux kernel. And then the moment you start sending such drop events to the CPU, a whole bunch of other things to protect the CPU needs to be in place. Instead of trying to reinvent all those things, what we did is we combined the SI TAM framework with the SI user-defined trap framework, which allows us to use a wide range of host type capabilities, which today already supports, which is used today for all our control plane protection features. Like you can do CPU queue selection, rate limit specific kinds of flows, and all this can be done. So we allowed the SAI TAM framework to reuse this host type framework. So combining this TAM and host type allowed us to do all this with minimal changes to the SAI framework. And this, the previous talk, what was talked about high frequency telemetry, also reuses some of the capability we introduced here. Now let's look at the other blocks that helps this standardization. The first one was these are all existing components and standards in the Linux and SONiC community. The first one was the devilling trap. So devilling trap allows us to standardize drop reasons and the reporting methods across ASIC vendors. So today, when a switch drops the packet in the data plane, there are different proprietary ways the device, the ASIC, informs its device driver. So that doesn't change. It can all be proprietary, but then the device drivers follow the devilling trap mechanism so that they can normalize the drop regions, standardize it across ASIC vendors. That's the purpose of this devilling trap. It standardizes the drop regions and the way the drop regions communicated to the higher layer. The second part is there is the drop-on module in the Linux kernel, which allows user space or any application to subscribe to drop events that happen in the Linux kernel. So this allows us to standardize the reporting format and also have a uniform mechanism to get the drop reasons from both the Linux kernel stack as well as in the hardware data plane. Lastly, SFlow version 5 has support for drop packet notifications. So that standardizes the drop reasons across operating systems. It's a standard that will help us standardize it not just within SONiC, but across operating systems. And it uses standard SFlow version 5 datagrams to encode this drop notification. So this is the three pieces what we want to end up supporting different types of ASICs and report that in a format that is uniform across not just SONiC, but across different network operating systems. And all this, if you look at all this, the software components that implement these standards, right? These are all already existing and they naturally couple with each other. That creates a easy, smooth pipeline. Now let's see how we are putting these components together. SONiC has something called an HSLOD agent that runs inside the SFlow container. So the HSLOD container will now subscribe to the new GE netlink family called drop pointer. And when a packet gets dropped in the Linux kernel software stack, the Linux kernel generates a GE netlink message which has all the following information. It has the packet payload. Along with it, it has information like what was the source port on which the packet came in, the drop reason, whether it's hardware drop or a software drop. What are all the drops generated by the kernel stack will have it as the software drop. And then the reasons, timestamp, all this information will be sent from the Linux kernel. This is all done by the Linux kernel drop-on module. Now, if a packet gets dropped by the switching ASIC, the switching ASIC has proprietary means to inform the device driver, and the device driver then generates another generic netlink message on the same drop pointer family, and this will have the usual same, almost similar to whatever was the message that was sent from the Linux kernel. The source, timestamp, all this would be there. Something extra is the hardware trap name. So this tells a reason, the device specific reason why it got dropped in the hardware, and this using devilling, as we talked about earlier, the devilling trap makes sure this trap name is consistent across vendors. Each vendor could have different reason codes, but the devilling trap would have standardizes like a black hole route, or it could have been an ingress STP filter or a VLAN tag mismatch, right? So these are standard drop reasons define the devilling trap, and that's what will be standardized in whatever is the generic netlink message just generated, irrespective of the ASIC type. And now, when all these messages come to the HSFlowD agent, the HSFlowD converts this into SFlow version 5 datagrams. So the HSFlowD has support to understand what is there in the deblink trap and convert them into standard SFlow drop reasons. So this becomes the standard SFlow drop reason message. So what we see is all this can be leveraged by using proven Linux. All these tools what we're talking about already exist in Linux, and they have natural support for what we're talking about. So using this proven and deployed solutions, we can create a standardized framework. And I'll let Madhu talk how we are putting this all together at SONiC.
Thank you, Ravi. Thank you so much. I think you covered a lot. Thank you. So I think this is a high-level, SONiC drop notification architecture. I think this picture speaks volume, and it is more familiar with you all guys. And so I would like to call out two important points here. So the first point is SFlow drop notification. We leverages Linux native drop infrastructure, drop monitor infrastructure. So you can see CR lines which is depicted here. So that's there, which means you get both ASIC as well as kernel drops, homogeneously and it reports. So that as a network operator, you have unified visibility into both your ASIC workloads as well as ASIC endpoints as well as Linux endpoints. So second important thing I want to call out is unlike SFlow, which is sampled, whereas drop monitor notification, which is rate limited for a good reason, and it is being handled in CPU, where the normalization will happen from vendor dependent codes to independent codes. And if you look at the architecture, it's a bunch of containers. We are not reinventing the wheel here, so we are extending this architecture to support drop notifications. And so I would like to call out there are a couple of containers, SFlow container and sys service, and also SINCD container, and also ASIC driver. The SFlow container, which essentially have a main agent which understands the SFlow configurations, and so basically it provides both normalization, also communication layer to the controllers. Whereas RAIDS is the centralized database where it captures all the configuration. Whereas sys service, which have SFlow orchestration, essentially it subscribes to SFlow application tables for drop monitor management as well as packet drop notification sessions being established. And sys actually act as a southbound interface to overhaul to all multi-vendor ASIC. And the SINCD essentially use TAM telemetry management APIs, monitoring APIs to program low-level ASIC drivers. And if you look at the flow, the orange lines depicts about configuration flow, whereas CR lines depict about the drop detection and notification flow. As a network operator, we can use CLI to configure SFlow drop notifications. We provide also SAI capability to check whether the ASIC have the drop more capabilities. And as soon as the instrument, essentially the configuration will be stored in Redis for persistence, and it also simultaneously invoke post-flow service to basically to set up all the SFlow drop configuration, drop monitoring sessions, and also which uses this is the configuration for notification limit and everything will be set it up. Whereas sys service having a SFlow orchestration, which uses telemetry and monitoring API, which essentially manage both drop monitor session handling as well as the rate limiting. And when it comes to the packet drop notification path, where ASIC driver detects the packet drops with the drop reasons, and also it applies various optimizations like rate limit for drop notification, and it uses a standard channel which is a netlink channel to unify both ASIC drops as well as kernel drops with more context about why and when and where it is getting dropped, and it's giving to just service, which essentially normalize and in SFlow v5 datagrams and ship it to a collector. Yeah. So this was so the ultimate goal was it is collaboration. There are multiple collaborations happened, and it is joint effort from Marvel, Aviz, EdgeCore, Innon, and eBay. And the ultimate goal was we would like to unify both ASIC and kernel drops using a standard protocols. SO is a well-known standard deployed across multiple vendors, right? So then where we are, right? So this HLD has been discussed in community and which is out there for feedback and suggestions, and we are tracking for upcoming release. And the second thing, the new packet drop notification structures essentially enhance the visibility into the packet drops, where it essentially tell you where and what reason for this packet drops. And there is a SFlow tool. Inmon provides this SFlow tool, which is a lightweight Linux tool where it can convert SFlow V5 datagrams into human readable format. Essentially, as a developer or network operator, you should be able to use this to understand where and what the packet drops can occur, right? And finally, we have a SAI TAM API, which is out there since 2024. And thanks for Marvel. I think they come forward, they're implementing SAI TAM API, and I would like to request more and more ASIC vendors to participate and to bring in unified visibility into the packet drops. And I have a couple of things, call to action items. Since it is SAI TAM API, which is out there and which is being materialized and matured, and I would like to call for more and more ASIC vendors try to implement the TAM API and provide more visibility into packet drops. And so you are free to inform as much as packet context around the packet drops, and try to implement the standard Linux interface so that it could be a common unified way of reporting the both ASIC as well as Linux kernel drops. And so SFlow side, we are requesting Inmon team to support more and more. Today they support around 200 plus packet reason codes. And as and when we have more custom codes, we would like to ask Inmon team to enhance as much as possible in SFlow V5 drop. And so for any reference implementation, you could reach to me and also Marvel, Edgecore, and Inmon. And so these are the couple of I have. So this Inmon has provided this nice tool, which essentially convert the SFlow drop notifications into a nice human readable format, and you would see packet drop notifications and also along with sample flows. And we would like to call for more and more visualization tools so that it would be really helpful for network operators to have a unified visibility. And with that, thank you so much for all collaborators, and we are looking for more and more ASIC vendors participate in that and to kind of bring in unified visibility into both ASIC as well as the next kernel packet drops. Thank you so much. Any questions?
Hi. So Madhu, the net here.
Hi.
Yeah. So the Netlink monitor channel you spoke about, right? So the couple of Netlink messages you have shown. Those are predefined the existing ones, or it's a new Netlink message format that we are introducing?
Yeah, these are all existing. That's a Linux sub module called drop1. So it has defined all this message. It's just one message type. Okay, and in a Netlink you can have generic Netlink, you can have attributes defined, right? So this all well-defined attributes in the existing drop1.
Okay, so the Netlink side implementation on the HSFlow side alone need to be done, and that will be upstreamed to the open source HSFlow.
HSFlow already subscribes, supports subscribing to generic Netlink messages, right? And this family supports also there in the HSFlow.
So in the V5 version, it's there already.
Yes,
okay. Yeah, thanks.